We have David Curtin, and we are moving away from the interaction point. We will hear about MATHUSLA now.
All right. So thanks for the invite, and thanks for this cool workshop and all these awesome talks on these experiments. So I'm going to give the latest on MATHUSLA, the current status and prospects. Okay. So this is the 10th talk or something, and I don't think we need much of an introduction for long-lived particles or free-will interacting particles. The sort of punchline is that they're motivated by analogy to standard model long-lived states, just because any new physics could be long-lived. And they're also motivated by the big problems of particle physics. And this is one of those sort of slightly crazy charts that shows you how, no matter what your high-energy theory religion, you should care about long-lived particles. Now, the LHC is a crucial machine to access long-lived particles because it gives you both intensity and mass reach, so you can access higher scales. And the LLP search program at the LHC is booming, but as we've already had a discussion, you have to battle complicated backgrounds and trigger limitations, especially for long lifetimes. So this motivates a dedicated long-lived particle detector for the LHC, pardon me, with high acceptance and low background. So one of these possibilities was Anubis. MATHUSLA is the largest of these proposals because it goes all out on reducing backgrounds with shielding. So MATHUSLA is a proposal to essentially put a large empty box above CMS, and it's displaced about 70 or 60 meters vertically and horizontally, and partially excavated. And on CMS-owned land, there's this piece of farmland that CERN owns, which is perfect. And in this box, you have trackers, and the long-lived particle travels in there, decays, and is reconstructed as displaced vertices. And this large amount of shielding is our strategy for a near-zero background environment. So the collaboration by now is fairly large. Here is the latest sort of official publication by the collaboration that gives you a snapshot. The main experimental collaborators include people from all these countries. The TDR is in progress. There's been lots of delays in significant part because of COVID, not getting access to CERN and all these things, and having a lot of difficulty with ordering hardware and getting into labs. So we originally planned to have this out by now, but it'll be pushed back about a year. But we're going to have a TDR out very soon. This R&D is happening. And the idea is to begin MATHUSLA operation with the high-Lumi LHC. So just a very quick rundown of what's been happening in the last roughly year or so. MATHUSLA has operated a test stand above Atlas in 2018, and the results were published last year. And this is basically sort of topologically a mini MATHUSLA, but it's made of sort of random spare parts that were lying around. But it's very, very nice still because you can reconstruct downwards tracks in excellent agreement with cosmic ray expectation, and you can reconstruct the up tracks, and the upwards tracks, and this is done purely by timing, of the layers. So you go ding, 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 going all the way up. You have two components of up tracks when the beam is on. One of them is from cosmic rays striking the floor and liberating or backscattering something. And the other one is from the muons from the LHC beam. And both of them are well captured by simulation, which was a really, really nice result. And it taught us a lot about how to simulate the unique environment of MATHUSLA. Okay, so that's very nice. Last year, we published the letter of intent update, which summarizes progress since the LOI, which is a few years ago. And the main point is that we now have a somewhat realistic detector geometry. It's 1/4 the size of the original MATHUSLA 200 behemoth, but it's the same sensitivity because it's closer by sort of square root of 2 in all dimensions. So that ends up canceling. Not a square root of 2, a factor of 2, roughly. It's also a slightly updated detector design. We have simulators instead of RPCs, just because it's easier, we think, to go to high, lots of detector area. We added some more tracking layers to be on the safe side right now as we do initial studies. We might not need all those, and we might end up shift. This is all preliminary still. Like as part of the detector R&D, we will shift some of this around, but this is the current benchmark. And there are some background studies calibrated by test stand data, as well as the next steps. So MATHUSLA at CMS, very specifically, is going to be sitting, CERN owns the pink land, and Methuselah can be sort of right here, almost exactly in the location where you want it. If you move it over a tiny bit, that's fine too. And we did some preliminary engineering studies to make sure that there aren't any showstoppers to implement a modular design where you have these detector modules in this initial study. It's 10 by 10 modules, but of course that'll be optimized, and they're pulled in by cranes, like on a shipping yard kind of thing, and then sort of held by there. So it's sort of some fairly standard civil engineering, but no particular showstoppers there. And to the best of our knowledge, no Roman ruins that are hiding there. But of course, who knows? Here's a sort of 3D view of what this model, of what the current benchmark module would look like. It's sort of a 9 by 9 meter module. It has some flow detectors and these ceiling trackers. All of this is simulator right now. And this is a view of what the whole thing would look like. This may yet change as a sort of unofficial preview. It may be the case that we want to shift this a little bit to make the flow detector hermetic, because this will help a lot with background rejection to have a hermetic flow detector. So you might modify this a little bit, we might end up losing some layers up here, but adding something in the walls. So it's not set in stone. I want to make that very clear, but this is sort of the current benchmark. For the extrude scintillators, we're currently looking at bars that are sort of going to be half as wide as the module, and then you have sort of readouts on one end, you know, sort of 2 per module kind of thing, 2 layers of readout per module per layer, pardon me. Now, for the sensitivity, I'm actually not going to spend too much time on these because I think a lot of people have already seen these plots, but those of you who maybe have not, here's the sort of 0th order money plot where we look at Atlas sensitivity for Higgs goes to long-lived particle, where long-lived particle decays to hadrons. This is a situation where the Atlas muon system reigns supreme, but at the same time, there are some backgrounds in the muon system, so that ultimately limits you to be roughly here by the time that you have the high Lumi LHC. Methuselah at CMS would increase that by a factor of 1,000. So you get to the BBN limit and life is excellent. And you have sort of the usual comparisons between, in this case, Codex and Atlas and Methuselah, but we've already seen comparisons with Anubis as well. So this is a sort of standard story where these external detectors can improve on Atlas between 1 and 3 orders of magnitude for these decay modes. As part of the PBC study, we, of course, under sort of the direction of Gaia and the PBC, we did all these very nice comparisons for low energy long-lived particle models with low masses. Except here, we also look at Higgs decays for the standard model plus singlet. The only reason I'm flashing these is to emphasize that the Methuselah 200 curves are really, you know, we computed them for Methuselah at CMS, and it's identical. You can see the purple on the orange, on the yellow, except that short lifetimes, Methuselah at CMS is a little bit better because it's a bit closer. But it's, you know, for all intents and purposes, the same. So you can just reuse the Methuselah 200s in your thinking. And there's a very nice story about how Phaser plus Codex Blee plus Methuselah would allow the LHC to cover this parameter space really, really nicely. So that's kind of nice. Now, a really, really important caveat is that I think essentially all of these sensitivity estimates do not take reconstruction efficiency in the detector into account, and that is a very non-trivial topic that, of course, the detectors are trying to maximize with the design, but that has to be studied carefully. And the story, you know, okay, so if you want to see more for right-handed neutrinos, you have significant sensitivity along with many of the other proposals. And at high energies, Methuselah can probe Higgs xenos with lifetimes in the sort of in the TeV range, with lifetimes in the kilometer range. So you get very low masses and very high masses together. And that's the sort of advantage of using something like the LHC as your source. And as a very general point, and this applies to all the long-lived particle searches, it's really important to have in mind that long-lived particle searches really are also dark matter searches, yeah? Because in many dark matter scenarios, the properties of the long-lived particle in the primordial plasma control the dark matter abundance. That is the case, for example, for freeze-in dark matter. And in that case, long-lived particle searches can be our best or even only way of discovering dark matter. So that's a really important thing to have in the back of your head as well. When you think dark matter, you should think long-lived particle searches as well. So a few updates that are more centered on Methuselah on the theory side. Last year, my excellent student, Jared Barron, published a very nice paper where he showed that Methuselah can not only diagnose the new physics, detect long-lived particles, but it can actually diagnose them with very high fidelity. So specifically, MATHUSLA is planning to supply a level 1 trigger signal to CMS. So as soon as MATHUSLA sees some upwards tracks, CMS writes to tape, and then you go offline and you reconstruct your vertices in MATHUSLA, and then you look at those corresponding CMS events and look at the event information. Now, the purely geometrical information within MATHUSLA already gives you the long-lived particle boost, just from the geometry, and it also gives you the decay mode. I mean, with from an array of reasonable options, right? So based on multiplicity as well as the alignment of the tracks. So if it's leptonic, it's few tracks. If it's hadronic, it's many tracks, so on. And if you analyze this together with the main detector, you can use main detector information, and you will reveal the production mode. So we looked at the long-lived particle simplified models, and which kind of covers most reasonable possibilities, and you can figure out what the production mode is, as well as the parameters of the underlying model, like the parent mass, the long-lived particle mass, with about 100 observed events. So, if you say that in a background-free detector that 5 to 10 events is discovery, then going only a factor of 10 higher for parameter estimation is pretty awesome. That's standard, right? So that's really excellent. And these methods and results should apply to Codex and Anubis and so on. The main moral is these external long-lived particle detectors can analyze the underlying physics model in detail. There's an ongoing project that I'm actually currently working on with Rachel Nguyen, who is Yoni Khan's excellent student at University of Illinois Urbana-Champaign, as well as Joss Foster, who's now the MIT Pappalardo postdoc fellow, which is a secondary production of dark photons. So this is the original PBC estimate of the dark photon minimal model, where the dark photon is a long-lived particle. And as you can see from this yellow curve, MATHUSLA seems to have very poor sensitivity, because once you reach the lifetimes where the dark photon long-lived particle can reach MATHUSLA, the production rate is just too low, because production rate and decay are the same operator in this model, in the way it scales. However, this estimate neglected a high rate of secondary production of dark photons in the main detector calorimeter. Yeah, so you have QCD crap hitting the calorimeter, producing dark photons. This exploits the huge QCD rate at the LHC, which is not at fixed target levels, but approaches fixed target experiment levels, within some orders of magnitude, but much higher than the sort of high energy, collision only source. And it's kind of cool. It's a unique source of long-lived particles at the LHC, which is only available to external detectors because you're producing them in the main detector. There's probably some caveats to that, but it's certainly an obvious source for the external detectors. Maybe you can... anyway, so this is in progress. We've got estimates that show that this will dramatically increase the range of MATHUSLA. But again, the detailed calculations are underway, so you'll have to stay tuned. Okay. So on the MATHUSLA side, some updates on simulation and backgrounds. We have a full GN4 simulation for MATHUSLA at CMS, and certainly full in the sense that it should give us a fairly accurate detail of the kind of background we're dealing with, and more importantly, how to do realistic signal reconstruction and background discrimination. So we have the cavern access shaft, CMS, rock and detector are all fully modeled. The rock comes from a geological survey. CMS is a hollow iron cylinder because we don't do CMS simulation, but it should capture the material. This plot is information free, but I just like it. This is our simulation of W bosons or W and Z's producing muons, which fly up, and this is the upwards W muon hits in one of the MATHUSLA layers, and you can really see how you sort of spray these muons from the LHC interaction point, and there's a lot of them. We can reconstruct displaced vertices in MATHUSLA. This is for a sort of two vertex event, two-track vertex. So that's good. What we have noticed as we code this up, for real, is that we really MATHUSLA is a unique environment where it's big, and so spatial resolution is not that important because you have big opening, modest opening angles over 20 meters give you big separation. So spatial resolution is actually not that important. Timing resolution is still super important for cosmic ray rejection. But because you have a big volume, especially some tracks will wiggle around a little bit. And that's why spatial resolution seems to not matter that much. What matters much more is that you have good tracking algorithms that take it into account, like Kalman filters, and those are actually currently being implemented. So this is all early, but we're hopefully on our way to getting much more realistic results soon. Even so, and this is more from the test stand, we can estimate the number of LHC muons, both from simulation and from the test stand measurement, the test stand giving us confidence in the simulation. And you have, again, 10 to the 8, something like 100 million muons from the LHC. So you need a real, so this is not an irreducible long-lived particle background, but at that high level, you really need a honkin' excellent background rejection. And I mean, so a little word of warning for Anubis, this is going to be orders of magnitude larger for you because you guys don't have 100 meters of rock. And, once you have that many muons, a few of them do interesting things. So we have demonstrated within our simulations, although I cannot show this yet, that we can reduce this down to 0, but we might struggle if we had, 2 or 3 orders of magnitude more. So this is quite a lot of muons. Anyway, so we are still finishing up our full GN study, but we also want to incorporate the custom tracking algorithms that are going to be used in the unique MATHUSLA environment, which is going to allow us to do this correctly. A brief word on cosmic backgrounds. There's not much to say here. The test stand confirms the theoretical expectation, and it also gave us an estimate for the number of upwards tracks that are just sort of single particles that are traveling upwards from the cosmic rays. None of these are likely to be long-lived particle backgrounds, so we're not too worried. The possible exception is K-longs, which are produced, unlike Anubis, which I think gets most of its K-longs from the LHC muons tearing through the walls. We get probably most of our K-longs from cosmic rays hitting the walls. Again, we think we'll be able to handle that, but we are currently working on the full simulations. Atmospheric neutrino backgrounds. This was a problem that we thought about a lot in the early days, and we don't think about it anymore because early estimates told us that we would only have order 10 events that you could veto with a timing cut, and that has been borne out, and it's even better in the full simulations because the early estimates were overestimates. So neutrinos are totally vetoable, and we are not going to worry about it from MATHUSLA. Well, we're going to worry about it, but we don't have to worry about it compared to the other things that we think about much more carefully. Okay, some brief update on cosmic ray physics. MATHUSLA has a secondary physics case, or a secondary physics sort of freebie, which is cosmic ray physics. Because it's our main background, we are in fact possibly an excellent cosmic ray telescope. We have a MATHUSLA cosmic ray subgroup with a lot of colleagues from South America and Italy, mostly, but also elsewhere. And the cosmic ray physics case white paper with full Corsica simulations is in the final stages of write-up. Just to give you a very, very rough feeling, MATHUSLA by itself could do very interesting cosmic ray physics. It would do even better if you add an analog RPC layer to avoid the problem of scintillator saturation when you have very many cosmic rays, particles in these high-energy showers, which are from a cosmic ray perspective the most interesting cosmic rays. For long-lived particles, these guys aren't a problem because you just blank the detector while they're happening, and they're like a sub% fraction of the time, so it's no issue. But if you want to analyze them, it's good to have an analog readout layer. So basically, the cosmic ray physics case is looking at the motivation and how much you would buy from this. The basic story is the more energetic, cosmic rays are created by primaries hitting the atmosphere and making a shower. The more energetic the primary, the more particles, and the wider the shower. And the geometry of the shower also depends on the type of the primary, if it's a proton or an iron nucleus, for example. And the main takeaway is that MATHUSLA, with this minimal configuration and without particle ID, whoopsie daisy, will in fact be able to diagnose the energy, the composition of the cosmic rays, and it would allow us to test, to do a lot of basic cosmic ray astrophysics, and also things that would help other cosmic ray experiments like hadronic interaction models and studies of shower structure. And there's a lot more info in the LP9 slides by Juan Carlos Arteaga Velasquez. Okay, a few last words on hardware development. We have several ongoing R&D programs in parallel within the collaboration. The main focuses right now are evaluation of different fibers and SIPMs for the scintillators. The scintillator bars themselves, where we look at geometry, timing, and dark counts. some preliminary design in detail for the data acquisition systems in the trigger, and then overall systems integration. And sort of two things that I want to show, which are again, a lot of that is still a bit early, but two things that are very nice is one on the simulator front, an absolutely critical design goal for our detector is an excellent timing resolution. Like I said earlier, spatial resolution is not actually that important. As long as you get centimeters, 10 centimeters, it's totally fine. Spatial time resolution has to be nanosecond or better. And this was recently achieved with a fiber test setup that is sort of on the scale that you'd put into this MATHUSLA. So we are getting sort of in this initial test 1 nanosecond timing resolution. So that's great. So that's a relief, and not that we didn't think that could work, but it's nice to see it work. Also, the folks at SLAC, specifically Larry, J.D. Russell, and Charlie Young, Larry Ruckman, have been doing some detailed work on how to put the DIQ and the trigger system together. The short story is that there's no problem with incorporating this into the CMS trigger, and all the, you have to design this and put it together, but all the hardware requirements, data storage requirements, bandwidth requirements, it's all sort of very okay in terms of what we can do. It's not a sort of super high rate experiment. You can solve all the data without triggers. We have a trigger system in MATHUSLA in order to trigger CMS, but we're going to be saving all data all the time. And then analyze it offline. Okay, so let me wrap up. An external long-lived particle detector program at the LHC is required to probe deep into long-lived particle parameter space. MATHUSLA offers the greatest and the most versatile reach. And in general, whenever you think long-lived particles, you should think dark matter. And there's been significant progress within the MATHUSLA collaboration on the hardware side, the software simulation side, custom tracking algorithms, and cosmic ray physics case. And we always welcome new contributions. So if you're interested in joining, or if there's people that would like to contribute their expertise, please let us know. That's it. Thank you.
Thank you very much for this nice overview. So questions? I see Jean-Loup raised his hand.
Hello, Jean-Loup.
Jean-Loup, you're still muted.
I can't hear you.
Yes,
Do you want to try?
Maybe
in the chat, yeah.
Or like plugging, or like deactivating your audio and back again. Bluetooth can be weird.
May I ask a question?
Sure.
Can you show the slide number 12?
Sure.
12. Yeah. What's the difference between these regions? I mean, it's standard model plus color, yes, and the excluded regions are the same, but the sensitivity regions are absolutely different. What? No, not absolutely, but I mean, is rescaled.
Yeah.
What is the?
So in this plot, so if you look at standard model plus singlet.
Yes.
There is a minimal contribution to the mixing of the Higgs with the long-lived particle, not the mixing. No, it is the mixing. So this minimal contribution will give you the B, mostly the B, but other stuff too, decaying into the long-lived particle via this Higgs long-lived particle mixing.
Okay.
However, whenever you write down this Lagrangian, there is a different parameter, which is the singlet squared Higgs squared portal. So that is not uniquely determined by this mixing angle, because there's other parameters, but it is one that is expected to be there. It's dimension, it's dimension 4, it's renormalizable, no symmetries can forbid it. And even a tiny amount of that will give you Higgs decays to this long-lived particle in excess of the expectation of the mixing angle alone, is the point. And this plot was just a demo to show that, but of course you cannot uniquely relate the mixing angle to the exotic Higgs decay branching fraction. But here I think we set it to like 1%, because that's kind of a reasonable thing that can easily happen. And then it just shows how you can probe much larger masses and a much larger rate at the LHC experiments, just as a demo. But this region would shrink or expand depending on what the exotic Higgs decay branching ratio is. And that's not something that you can relate one-to-one to this mixing angle necessarily.
Yes, we assume the 1% was assumed to
1%,
be
yeah.
the precision on the invisible Higgs width.
Oh, good. Yeah, yeah, very good.
This was the idea.
Very good. It's just a useful benchmark.
A reason reached by the end of, I think, high Lumi. Because at the moment it's 13%, I think. The accuracy.
Yeah. Oh, John Loop questioned, you mentioned that Methuselah can be used as a trigger for CMS. Is it fast enough to do that? I'm worried by the delay caused by the speed of light. So there's two reasons why it's okay. Well, there's one big reason why it's okay. And that big reason is that as part of the high Lumi LHC upgrade, the CMS computing is all going to be moved to the surface. So the trigger farms on the surface, which makes it very easy within the relevant difficulty level of doing any of this. But we spoke to the CMS trigger conveners and trigger experts, and because the triggers are on the surface, the trigger farms on the surface, it's easy to wire Methuselah up. It'll be physically very close by.
Thanks.
Oh, now we can hear you.
Yeah.
So if I can, if you go back to the test stand results that are clearly very nice.
Here.
Where you compare exactly up tracks. You know that we always commented about this plot saying that this is a huge amount of tracks given the smallness of the prototype. So if you can multiply this amount of tracks for the Methuselah side, so are you really confident that you can control the background?
Yeah, so like I said, so I am confident. Let me kind of give you the sort of unofficial reason why we're fairly certain. So the absolute number, let's see here. Okay, so
yes, it's this.
most of these up tracks are very low energy electrons and protons mostly, and some muons that get kicked up, right? Now, for sure, there are a very small but important number of things like K-longs, and we're simulating those and we're working on it. But we think we can deal with those, but that's not a huge number. This is a large number. This is the number of up tracks you'd expect at Methuselah. Yeah. But these are all single low energy tracks that don't point back to the displaced to the IP. So one way or the other, we are not very worried about those. This is only 2 orders of magnitude less, and this is actually high energy muons.
Yes.
So those are more likely to give you a secondary shower or other displaced vertices. And indeed, we are seeing this in our simulation that, of course, these have a rate of producing a displaced vertex. Yeah. Now, again, that is vetoable because you have the flow detector. You even maybe can use the CMS main detector, But the point is that these guys have a serious chance of making displaced vertices because they are so high energy. These are all sub-GeV single charge particles, so we are less worried about them. Ultimately, we will demonstrate all this in simulations. This is a number. We have simulations lined up. This is a number that is still capturable by simulations to some extent. So that is being studied in detail. This is just to say, if I was worried about single tracks faking displaced vertices, I'd be worried about the W's more than these. But even the W's, our initial studies have shown that we can cut them, but we want to do it better with the better tracking. So anyway, so these are all valid concerns, but we are fairly sure that we can do it, and our initial studies are pointing in that direction, and we'll show those as soon as they're a bit more polished. Yeah. Oh, sorry. What I should say, all of this, however, drives the design of the detector. So the benchmark I showed you is a bit naive in some ways. What might end up happening, and I know I'm being recorded, so I should speak as just very unofficially, but what might end up happening is the number of layers for tracking might not be that important. But things like extra layers for vetoing might be more important. So we might shift some of the budget around. And that might that might tweak the design in the next iteration. But the focus is going to be making sure we can reject these backgrounds.
Do you have an estimate of the cost? Because you didn't provide anything.
that'll be supplied as part of the TDR.
Sure, sure.
But
sure. Order of
but-
magnitude. Now that is smaller.
So the civil engine, yeah, it's smaller. So the civil, so let me give you the orders of magnitude.
Yes.
The civil engineering, the unit of measurement for civil engineering is $10 million times a number.
Okay.
Tens, yeah. The unit of measurement for the readout is $10 million times a number. The unit of measurement for the simulator, which can be produced very efficiently at the extrusion facilities, is $10 million times a number. So maybe that
this
number
number is what? Because if it is
No. But what I'm saying is that number is not 10. That
Okay.
number is 1 to a few. Okay.
Okay.
So that is to say, if you add all that together,
Yeah.
I would say we are still aiming for significantly below 100 million. And that is backed up by the initial pricing estimates from Fermilab and by the initial engineering studies by CERN. But again, I really want to emphasize that this is not an official statement. And,
No, I agree.
you know, so TDR we
say.
have that in progress, but I really want to be careful here. But again, the story hasn't changed. But making it smaller was a very important part of that story.
Sure.
Yeah.
Okay, so let's move to the next talk then. Yeah, thank you very much.